So now let's look at the fundamental theorem of calculus, part 1. So first recall the Riemann sum and definition of definite integrals. Here's a definite integral definition. So when you look at this, that means this limit of sums. Excuse me. So the limit of sums is what this notation means. And so essentially what we're going to do then is use a theorem to have a way to calculate this without actually taking this limit. This limit is normally like ridiculous to take. Like you don't take a limit of whatever this is. But check this out. So the theorem says if f is continuous on a closed interval from A to B and capital F is the antiderivative, just like we've been doing before. So it is an antiderivative of little f on the closed interval from A to B, then the definite integral from A to B of f of x dx, right? That's the limit of sums, is equal to the antiderivative of f of b minus the antiderivative of f of a. So essentially, all you end up having to do is find the antiderivative of little f and then evaluate it at the endpoints and subtract it. So it's making the connection between the antiderivative and the derivative. Really an incredible result. So let's see how to apply that. So I'm not going to get into the proof of this, but just to give you an idea, what you basically are doing then is if you have some curve and you're looking at, so like from A to B, you're looking at this this area right here. This is kind of a rough idea. If you're looking at that area, essentially it's like saying there's some place in here, like when you add this up, that you can find, like right there. If you add up everything underneath that, it's going to be the same as if you added up everything else. I'll show a better example of that later, but well, that was kind of cool. I didn't realize I did that. You see that erasing thing? Anyway, I'm not going to get into that concept as much as I want to show you how to use it. You got to leave the class with knowing how to do definite integrals and more antiderivatives and finding area between curves, that kind of thing. All right, so let's look at an example how to apply this. So it's an evaluate question. So evaluate the definite integral of 0 to 3, 16 minus x squared dx. So it's one thing to look at is think about, if you look at y is equal to 16 minus x squared, what is that? Well, that's a upside down parabola, right? That's a parabola that shifted up 16 units, and it's basically like that. And then we're evaluating that from 0 to 3. So it's this area is what that ends up being. Now, it's only area, realize, if it's if your f is positive in that region on A to B. But right now we're just calculating. We're not worrying about the meaning yet, just calculating. But I always want you to keep track of what does this mean. Okay, so this equals, so what you need to do then basically is calculate the antiderivative, right? Now you don't have to show this, but your antiderivative, capital F of x, is what? Take the antiderivative of that. Now that's just a polynomial, so that's pretty easy to do. That's just 16x minus 1/3 x cubed. Right? Take the derivatives and you get that. You sure do. So you just say this is equal to capital F of 3 minus capital F of 0. You always remember that. It's always B minus A. B minus A. Always top minus bottom. Right? So you're going this way. So you evaluate that. So you normally go right to this step I'm about to write. You just write it down. And this is some of the notation you write. You do the antiderivative, 16x minus 1/3 x cubed. And then you use this evaluation bar, or you can, 0 to 3. And then now you substitute that in. So that is, let's come down here, equal to 16 times 3 minus 1/3 3 cubed, and then that's minus 0. Minus, and then this next part will be minus 16 times 0, which is, of course, 0. So the rest, this is just a polynomial. So, of course, when you plug in 0, you're going to get 0. So that's just 0. So you get 16 times 3 is 48 minus, and then one of those 3's reduces, so that's a 9. So it's 48 minus 9, which is 39. So the answer to that is 39. You get a value, right? You get a real number. Oh, what happened to the plus c? How come I didn't put plus c in here? And actually, I'll show you that on the next one. Let's do this one, and then I'll show you where that plus c, why that plus c goes away. So evaluate the integral from 0 to pi halves. Put some trig in here. Let's just do sine x dx. So now what you do is you calculate the antiderivative. The first thing you do, antiderivative of sine x is minus cosine x. And then you evaluate that. Oh, let me suppose you did the antiderivative and you said plus c. Okay, so now you evaluate from 0 to pi halves. So when you substitute in and subtract, you get minus cosine pi halves plus c minus negative cosine 0 plus c. And then you simplify. It's equal to cosine of pi halves. What's that? That's 0. So it's 0 plus c minus negative 1 plus c. So it's c plus 1 minus c equals 1. So that's what happens essentially, is the c's cancel out every time. So this c is not needed. You don't put plus c when you're doing a definite integral. When you have limits of integration, it's going to always cancel out. So we don't have to put it. Indefinite integrals, we must put a plus c. Definite integrals, you do not. So that area under the curve is 1. So that was sine from 0 to pi half. So basically, you have your sine curve, and then you're looking at this area. The area is 1. Okay, but we'll get into more of that in a bit. Let's see. I have a couple more examples on here. I'm not going to work them out. You try some these on your own. These are, I think, from the book. So do the definite integral from -2 to 3. So if you have just a polynomial, it's pretty straightforward. You just do the antiderivative and then substitute in. Okay, so try that one. Don't look. I'll write down the answer. Okay, next one I do want to show you. It's 105 over 4, 105 over 4. Next one has a variable in it. So if you put, or we call it a parameter, right? It's a parameter. So 0 to b. And then what happens? So sine x minus cosine x dx. So you take the antiderivative of each of those and then evaluate. So you do the antiderivative of sine is negative cosine. And then of cosine is sine. So it's minus minus. And then you evaluate from 0 to b. It's always b minus a when you do that. So you substitute in and evaluate. So it's equal to minus cosine b minus sine b minus negative cosine of 0 minus sine of 0 minus cosine b minus sine b plus 1. So you would just leave b in there like that as your answer. All right, the next part is the fundamental theorem part 2. So this one says if f is continuous on the closed interval from a to b, then for x in AB, d dx, so the derivative of a to x of f of t dt is equal to just f of x. So what this looks like when you're doing a antiderivative of that, you have some function f of t, and you're on, say, a to b. Then that is a to x f of t dt, like that. And so when you take the antiderivative of that, you get just f of x. You get, so it's like there's some value in here. Oops, I did that little wrong. There's some value that gives you the function, like right here. So if that's x and you go up to the curve, you get just f of x. But essentially, it undoes the derivative. The antiderivative. So if you do the derivative of the antiderivative, you get just f, is what I want you to remember. This one's not used quite as much, more in theorems and proofs. Okay, we'll do. So the next section, couple sections, or is it just 5.5? I think it's just 5.5. I'll double check that, but the next section is really the meat of heart of what you really need to do. Like this, this is more theory stuff, and I need you to know it. Go through it and understand this fundamental theorem, and go through it, but and just calculate it. Right, do the calculations. But you're going to use it in the next section. You have to know the next section. So the theory, we like to show you all that, and that's what we like to do. But 5.5, you got to be able to do 5.5. It's going to be use substitution and applying these concepts. So let's get into that next video.